Thank you, Suvan. Can everybody hear me? People in the back? It's fine? Okay. All right. So I want to start by acknowledging that we are going through a lot of turmoil in the world today. There's a senseless war in Ukraine. I hope that stops soon. We're also just reeling from the aftermath for the last 2 years of COVID. I hope that somehow in the next few months, it'll subside and we'll get to a new normal. But I cannot contain myself. I am thrilled to be here. Thank you to Suman for those nice words. In fact, I was in the audience when Suman gave this Rockstar Award to Lin Zhong a long time ago. And I couldn't for the life of me think that I'll be here today. Thank you to the HotMobile community. It has been a very, very supportive community. Thank you to my students, to my mentors, my letter writers, my collaborators. I will thank them all in the end more formally. Also, thank you to my family, my parents, my brother, my grandmother. They've been super supportive all through my years, but most of all, thanks goes to my husband, Niranjan, and my daughter, Nila. They have made my life super joyful. They've supported me through all of these times. And so I'm very, very thankful to have this family. So actually, when I got this award, Niranjan was very happy and he was talking about this nonstop. So at some point, my daughter had had enough and she said, Amma's not a real rock star, right? Like, look at her. So thanks to kids to keep us grounded. But anyways, the lens for this talk I'm going to use is I'm going to talk about the evolution of 3 research threads that I have been working on for over a decade now. One of them is on web. The second one is on energy. And the third one is on accessibility. So usually you would know about research. The seen aspects of the research are the papers that you publish and the presentations you make. But then there are many unseen aspects of research, right? So this is partly inspired by a podcast I listened to called The Seen and the Unseen. So what I want to do today is not only talk about the papers, but talk about some of these unseen aspects. Like, what was the motivation for the project? How did we start working on this? What are the challenges and joy in doing many of these interdisciplinary work? Because as I would describe, all 3 works have an interdisciplinary angle to it. What's the role of serendipity? So this talk is going to be both the seen and the unseen that way. So let me start with the web. So this project actually started back in HotMobile 2011. I saw a talk. This was by Lin Zhong and his students, Jen Wang, Felix, and Manzoor. And the talk was about why are mobile web browsers slow, right? And the reason this talk was intriguing to me was that up until that point, I had paid no attention to browsers. I was using browsers. I never thought, oh, is this good? Is it bad? Why should it perform well? Blah, blah, blah. And so when I saw this talk, I was intrigued. And serendipitously, at that time, I had just joined Yoda as a postdoc, and there was a student, Sophia Wong, who had done some web work. She had gone to Facebook and done some web work as well. And then Google was next door. And Ben, who's here, and Matt Welsh were starting a group doing web performance. And so it seemed that, the universe was conspiring for me to start working on the web. So I got very interested in doing this and started looking at it more carefully. And in fact, one of those big motivations, I have to be truthful here, was just, why is this hard? For me, you have objects, you place it on the screen. Why should it be hard? All right, so let me give you an example of why this is hard. Okay, there are, what I'm showing over there, let me see, I had this thing. So there are 2 scripts here. The one on the top is loading a JavaScript called B and then loading an image, okay? And the one in the bottom is loading an image first and then the JavaScript. They're both loading exactly the same things. They look the same exact. Now, how many of you in this room think that the first script will load faster than the second? Show of hands. How many of you think that they will load exactly at the same time? Okay, all right. So it turns out that actually something happens here, where even though these 2 scripts are about the same thing, they don't load at the same time. And the reason is Let's see what happened in the first case. You would first load your HTML, you'll parse it, and then you load your JavaScript. After you load the JavaScript, you load the image, right? So it takes some amount of time. The second example, you again parse your HTML, load your image because that's the second tag, but then you load the JavaScript in parallel to this image. And so it takes much less time. Why? Because HTML parsing has a dependency with JavaScript because they both write to the same object, whereas this doesn't happen with an image because there is no write conflict. Now, this is just one example. Now, the reason this example is important also is that, like, let's say you are a web developer and somebody tells you you should improve your JavaScript and that will make your web page load faster. You do the second, you've written your code in the second way, and you change your JavaScript, nothing happens because there's no dependency. Right? And this is just one example. Like I said, there are many, many such dependencies. It depends on write conflicts, it depends on policies, and so on and so forth. And so dependency analysis is really key to understanding bottlenecks, right? And this is one of the reasons why you see these conflicting advice on the web on how to improve your page. Oh, make your JavaScript asynchronous. No, don't make it asynchronous. No, why? Because there are all of these complexities. So what we ended up doing was we did some black box analysis. We basically would load a page and then add a delay to it and do all sorts of things like that to extract out all of the dependency policies that the web page a browser might have. We did this for multiple browsers. And then once we have that, you don't have to read that. It's just showing all of the policies. You would build a dependency graph, which will tell you, here is what your page load will look like, and the red would show the critical path, which is what you need to be improving if you want to improve your page load time. Right? And so we published this, and actually, one of the interesting, neat things, I'll tell you a lot of neat things that came out of it, but my student found this discussion online from Google engineers. I'm not sure why they were discussing on a public forum. But anyway, so they were discussing about this work. And one of the things, for example, they say this paper is super interesting. A dependency graph is a powerful tool. And this really made my students weak, I think, after we saw this. So, okay. So once we built this tool, we became Yoda for a while. Okay, we started saying, okay, now I have this powerful tool. I can answer a lot of questions on the web. For example, I could say, what's the bottleneck on a mobile web page? Is that the same as desktop? It turned out that it wasn't. Okay, on the mobile, the bottlenecks were very different from the desktops. And then we answered a few other questions, but then eventually, and this was a lot of fun because we were unearthing things that were mysterious before. But I sort of got a little bored of this. And so I wanted to do two things. The first one was we wanted to make this tool usable, right? Other people would have better imagination than us to do other things with this. For example, our tool looked like that, right? It was a bunch of XML file that you had to go and dig through to figure out what the dependencies were. The other thing was, at this time, I was mulling about this point about whether performance metric even represents your quality of experience, right? So for the first part, what we did was we built a visualization tool. We were not visualization experts, but so we had to figure out, okay, how big should the bar be? Should the bar have one after the other, and so on and so forth. We actually did multiple rounds of user study. And we wanted to make sure that we actually first built a standalone system, and everybody said nobody's going to use a standalone system. So we did this user studies with industry folks and in telco and so on and so forth who design websites. And eventually, we have a tool that works with the Chrome developer tool. We also made this available with other browsers. So one of the takeaways here was, to me, is when we first started this, the idea was we'll build a visualization tool, put it out there, and it'll be done. But then we realized maybe we should write a paper about this, right? And it was a good decision that we decided that we wanted to write a paper about this. Not so much because we got a paper out of this, but because it forced us to make the right decisions. It forced us to say, what does the user want? It forced us to make sure that we take into feedback from our user studies. Okay. So next question, what do users want? So at this time, I think there were lots of anecdotal evidence to show that the way that we were measuring page load time was not the right way to do this because a user might want things differently. And so, for example, I'll give you an example. So this is an Amazon.com page. It loads at 7.9 seconds, right? It looks fine. This is the onload. The onload was the metric back then, so I'm using that now. This is what the Amazon.com page looks like at 1.5 seconds, and it seems loaded to the user, right? And so really there was some 6 seconds of difference where that there's not really slow from the user's point of view. Right? Why is this a problem? Because you might actually spend your time trying to optimize the page when the page was fine. And the opposite is also true. Oh, sorry. You have gmail.com at 0.9 seconds. It says it's loaded. Clearly, that gmail.com is not loaded. Whereas at 5.1 seconds is when it's actually loaded. So as a first step, what we did was we wanted to see what a user perception would look like. So this was my student, Connor Kelton, who had just joined our group. In fact, he had come to work on machine learning and AI, took my class, and I somehow lured him into doing systems work. And what we did was we loaded a page, we took a video of this, and then we asked users to tell us when they thought the page is loaded. So this was the first version. We refined it after we talked to our colleagues in cognitive science on how to do these studies. But the first study, this is what we did. And then we'll get the user perceived page load time from them. So in essence, they will tell me, okay, I think this is when the page is loaded. And then a number of users would say that, then I'll take that number and say, okay, that is the user perception. What we found was that there is little correlation between the user perceived latency and existing metrics. The way that existing metrics, the way that they measured was using this onload event that was called the page load time, or they use something called speed index. This is a busy graph to read, so I'm not going to explain the graph. Just look at the correlation. The correlation between this user perception metric and onload, as well as with speed index, was low. Okay. So this was on the laptop, and so I'm just going to do a side story. So what about web performance on smartphones, right? Does this problem occur there as well? Is it the case that the way that you're measuring is not doesn't align with what the users want? So at that time, what we did was we did the exact same study that we did on the laptop. We did it on the phone, and we found that the UPLT did not match, and we submitted the paper. The paper got rejected. And the paper got rejected because the reviewers rightly pointed out that, the way that you were doing this study is not how users interact on their phones. So our assumption was that you will load the page, stare at it until it loads, and then you'll start interacting with it, which is what we did for laptops. You don't do that on the phone. You load the page and you start scrolling, right? And at some point you say, okay, now I'm ready to interact with the phone. So we took that comment, worked on it. 2 short years later, we actually built a system that actually could do. So the problem with the study was that we were making a video of the page load and showing it to the user. Now, because we had to be consistent, right? Every user had to see the same version, otherwise it's hard to compare. So how do you do this for when you can also interact? How do you make sure that you can actually have a video of the page load while interacting? So the idea that Connor had was that you would actually take videos of every viewport and then stitch them together in a way that you can move up and down and to do some background stuff. And that's how we did this, right? So the moral of the story is sometimes your reviewer too is right? Listen to them. Anyway, so we did this, and guess what? We found that actually this user perceived latency does not correlate with the page load metrics on the mobile devices either. So what I'm showing here is just an example, of course, is that in the beginning you have this onload. What onload says is that when every viewport is loaded, that's when it says the page is loaded. This is speed index, which is another metric, which says if the first viewport is loaded, it's going to say that the page is loaded. That doesn't work either. So what we did here was that you will let them scroll. And then we also did a few tricks. It was different from our original study because by then we were working with some cognitive scientists and they told us how to do these kinds of user studies. I'm not going to go into the details, but basically we implicitly figure out when you think your page is loaded and you can start interacting with it, right? So one caveat though, when doing this kind of interdisciplinary research is that it's hard to find a home. So this work, we did a bunch of other things here as well, right? We found how often do you scroll and what is the effect of scrolling and blah, blah, blah. And we sent it to a HotMobile conference. They said, this is an HCI paper. Send it to an HCI conference. We said, okay, we'll send it to an HCI conference. One HCI reviewer said, this paper is clearly a systems paper. There are too many CDFs. Okay, so it eventually found a home and I'm very happy about this. But yeah, just a note for those doing interdisciplinary research is it sometimes the one issue is that it's hard to find a home. Okay. All right, so now we know this, right? We know that the user perception doesn't really correlate with the way that we are measuring page load today. The biggest problem with this, of course, is that you might be optimizing for a page load that actually users don't care about. So, so this is, again, a serendipity story. There was a student, Ji-Hoon Ryu at Stony Brook. He's now a professor at SUNY Korea. And he gave a talk about using gaze tracking for something else. I was in the audience and I heard the talk and I thought, why not use gaze tracking to see if we can do something better with for this user perception metric? And so we got around that corner on the screen. We combined efforts with some professors in cognitive science as well as in vision. And apparently this is a known thing, right? It might be new to me, but it's not new to others. So that your human gaze actually consists of these rapid saccades where you're moving from one place to the other, and then there are fixations. And it's known that these fixations point to user attention. Okay, so for example, if you have multiple users looking at this one page and you take all of the fixation, you can actually see that there are parts on the page that have a higher user attention than the others, right? These are parts that most users are interested in. And there's one way you can actually do this is, apart from doing user studies, you also have these saliency models that tell you which parts are salient, where most people are going to look at. Okay, so what we did was, well, can we somehow map user attention to object importance, right? And say that, okay, if there's a user attention is high at some points, then, and I map it to, this is an important object, okay? And push those objects first, you probably know where this is going by now, is that you take these fixations, you create a probability map of the page, which is more probable to have fixation. And by the way, we don't do this online. So it's not that when you're looking at the page, we're looking at your gaze. That's creepy in my opinion. What we do is actually collect this information offline with some other users. And then later we actually started using saliency models to do this as well, where you can actually predict just from the page, what parts of the page people will look at. And so then the idea then was that we would take these fixations, we would take, and then we use this technique called server push. I don't know if you've heard of this, where you would push parts of this page first. Of course, you have to make sure that the page doesn't break, but we were well versed with web by then that we could figure out how to make sure that the page doesn't break. And we built this called web gaze. And so what I'm showing here is for just a freeze frame of a page. Actually, you can go to our website and you can see videos of different pages loading with web gaze and with other techniques. And the main thing is that with the web gaze, you see that more objects are already loaded. So the idea was that instead of waiting for some time and loading a lot of things at one go, you basically load the most important objects as soon as you can. And we did a bunch of user studies after that and figured out that actually the user perceived page load time does improve when you do this. Right? In fact, the interesting thing was the onload metric does not really improve with web gaze, because the onload metric is when every object is loaded. That's going to take the same time whether you load the important objects first or not, but the user perception did improve. So by then we had a very good working relationship with our colleagues. And so we wanted to do some stuff from the cognitive science point of view as well. So what we wanted to do is to say, even what is engagement? Right? Why should the user be engaged at some point? What does it mean to be engaged? So another reason, number 2831, why interdisciplinary research is hard, is that we just don't speak the same language. It'll be months of discussion where we're entering the room saying, what is engagement? Coming out of the room with nothing. The next day we go back, again, what's engagement? End of the day, nothing. I kept going on and on and on. But eventually, I think I don't think we've solved this problem by any means, but we've sort of figured out like some interesting things. For example, if you start reading text on the page, it means that you're engaged. Right? So that is an onset of engagement. So what we did was we built a reading detector. So on the page, can I tell whether you're skimming or you're reading, for example, right? And similarly, another thing we did was, can we study whether your engagement changes based on the order in which your page is loaded or the speed at which objects are loaded? So, so anyway, so these are some of the things that we did from the cognitive science point of view. So eventually, this, as a summary of this thread, we started with understanding how the web works. And then we ended with understanding, quantifying, and improving user engagement. It was a circuitous path. It took a while. But the thing is, I learned a lot, and it was a lot of fun understanding how our cognition works, for example. Okay. So that brings me to the end of the session. I'm going to next talk about energy. I'm not going to talk about energy quite in as detailed as the web, but I wanted to talk about some of the main points there. This is another thread that I've been working on for the last over 10 years now. And the reason I also want to talk about this is because there's a lot of parallels between this and the web work, in the sense that we started because we found something intriguing or complex, and we're like, why is something happening? Then we got into it to an extent that we were able to do some contributions in that area. We understood that area well. And then we started looking outward to see, okay, now that we've understood this, what can I make a contribution in a different area? And if so, how can I do that, right? So it's sort of the similar thread and a similar feel. So we started back in 2009. This was actually my first project on a phone. What you're seeing there is an N95 phone, Nokia phone. Couldn't do much with it, unfortunately, but there it was. And okay, so the backstory for this is that, this was my first project, by the way, with my husband, Niranjan. We've since worked together on many projects, but this was the first one. Because at UMass, you had to do something called a synthesis project, okay, where you take your area and then you take some other area and then work together. So Niranjan chose to work with my advisor, Arun, and he was working on these phones. And he found that the energy for sending data on 3G was not consistent. So for example, if you send this data with a packet schedule, right, you send something, wait for some time, send something, and so on, the amount of energy would be one, and then you send the same amount of data, but you send one after the other, it will be different, and he had no idea why. But anyway, they moved on, started doing other things. Then I was at Darkstool, which is a workshop that happens in Germany, in a castle. If you get a chance, you should go, it's very cool. And there was somebody from Nokia there. And so I was talking to them and I said, hey, we're seeing this weird phenomena. You know why this might be happening? And they said, oh, this is probably overhead. Packets always have overheads. So I came back and I was like, okay, there's overheads. So then we thought, the three of us thought, oh, maybe we should think about this a little bit more. So we did some more research and found that, in fact, if you look at this 3GPP standard state machine, the way that the power works is that when you send a packet, the y-axis here is power. So when you send a packet, you have to ramp up your energy, and then you use a lot of power to send the packet. But once the packet is sent, you don't go back all the way to zero. You actually go somewhere in the middle. Okay, this is called the tail energy. And then after a while, you go all the way down. Right? And so clearly what happens is that if you send a packet and then don't send it for some time and then send another packet, each time you're incurring this tail cost. But if you send the packets together, you're not going to incur this tail cost. So we did something about this. We wrote a paper called Tail Ender. This actually work became very popular. A lot of people took this up and built their own systems with this tail energy. And I'm pointing this out because I did not at all think that this paper was going to be big. When we were working on it, we were like, whatever, this seems like an interesting thing, let's write about it. So sometimes it's hard to predict the impact of your work. You don't really know. But anyway, the more positive impact from my point of view was I started getting interested in working with smartphones. Like this was my first taste of smartphone. And luckily enough, the very next semester I went to Microsoft Research. I was an intern at MSR, and they were working on this project called Maui. I'm sure many of you have heard of this project, and I got involved in that as well. And this was my first mobile systems project, right? I'd never done my PhD was more networking. This was one of the big reasons why I got into mobile systems in the first place, because now we actually had a real phone. You could make changes and write code, and there were lots of people involved in this who were very, very good. For example, there's Eduardo, there was Victor, Alex, Stefan, and Ranveer. And so it was a great group. I learned a lot. So it was a very fun project. A big reason why, like I said, I'm in this in the mobile systems area. And the question there that we were asking was, if I offload computation to the cloud, okay? So I have a program. I'm going to take part of my program and run it on the cloud. Can I save power? So now maybe it seems obvious. Back then, it was not at all obvious that if you do communication, the communication cost will be lower than the compute cost for whatever that part is. In fact, back then, we didn't even know how to measure power on a phone, right? At that time, MSR somehow got this device called a power monitor. If you work in power and smartphone, I'm sure you all used a power monitor, but that was, I want to say that this is the first paper that used a power monitor. And so we've learned how to actually measure power. We also learned how to figure out, without external intervention, look at a code and say, this part of the code should be offloaded, this part should not be offloaded. And actually, interestingly, unlike the tail ender work, where I didn't expect it to become big, this work, even when I was doing it, I knew it was going to become big. And so, by then I got interested more and more in phones. I started doing more work on smartphones at UW as well. And actually, I had a good understanding of Android. Like, I understood the kernel, I did kernel programming. So this is all very good. In fact, I threw out my iPhone and bought an Android because I wanted my phone to also be the thing that I'm working on. And so we did a bunch of stuff. I'm just going to talk about one work called Mobile Hub. So this was the opposite of Maui. Basically, Maui said, I'm going to offload compute to the cloud. Here I'm saying, I'm going to offload, or rather onload maybe, sensing to a microcontroller on the phone, right, to save power again. And one of the biggest contributions here was we managed to write and do some information flow tracking in the kernel to figure out when to offload and when not to offload. So yeah, so by this time, and actually even a little bit after, I'm fully entrenched in mobile systems research. I've been doing it for a while, doing a lot of energy measurement. We have like 5 monsoons in the lab. But then what happened was that I got into this new topic, sustainable NLP. So this was again started by my student, Chin Chow, who's a postdoc right now at Yoda. And Chin is an expert in systems and NLP. So he's co-advised by me and Niranjan, who does NLP. And we've been doing a lot of work on how do you do efficient NLP? How do you run complex NLP applications on the phone? And so he came to me one day with this paper. This is a very, very nice paper from Emma Struble and others at UMass. And their paper showed that training in terms of carbon emission, okay, training an AI model takes 2 orders of magnitude more carbon emission than an air travel from New York to San Francisco. And so, and from our work on efficient NLP, we knew that so that is from the global point of view, but even from the inward point of view, if you're trying to run a really large network on your phone to do inference, you're going to run out of power very soon. So what we wanted to do was, can we do accurate energy estimation? Because that's critical, we thought, to do what-if analysis, to say, what should I train? Should I train model A or model B, which is better? Or should I run model A or model B on my phone, which is better? And I need to do this not with 2 examples, but hundreds of examples. And I need to be able to figure this out, right? And so what we did was, we said, okay, let's look at how, what existing energy models exist for NLP. So they had a model, but unfortunately, and this is a busy graph, so I'm not going to go too much into detail, but the y-axis here is the average energy error, right? And the x-axis are a few models, NLP models. The error was very large. And it was like sometimes 65%. And this was large because of many reasons. First, they were using power counters, but we know in the systems community that the power counters need to be calibrated to your hardware. They were also using the resource as a way to indicate how much power something takes. But again, there's been countless HotMobile papers that talk about how you can't really use resources directly. There are also like non-resource utilization when you when you are running an application. You can't just look at the start and the stop of the application. There's power consumption otherwise as well. And so we've done a lot of work that tells us exactly why this model is not working. So what my point was that systems research is uniquely poised to solve this exact problem. We've been doing this for years on end. So we should be doing this again to figure out how to build a better model. However, the catch was that we need to build interpretable models for the NLP domain. By that, I mean, so ultimately, what do I want to do? I want to reduce power or help somebody make a choice about how to reduce power. Right? So the way to do this would be that you would look at a model and say, okay, this part of the model is what is taking so much time. Or if I replace this with another, then this is how much energy it will take, not time. So this means that you had to be interpretable. So what we ended up doing was build an interpretable model called Irene. And the idea, again, actually came from another work that we were doing where we were trying to perform energy for web loads. So the idea there was that let me take this model, split it into its components, and then I will find the energy consumption of split it in a way that, you have this machine learning primitives in the bottom, and then you have your modules on top. And so you can predict the energy of the machine learning primitives. And one advantage is that every model uses the same primitive. So you can actually use the same prediction. And then you sort of learn how to build it on top so that you can actually figure out what the total energy consumption is. And this makes it interpretable because now you know which parts consume how much power. So of course, there's many other things that we had to take care of, and about like the models may be different, the runtime may be different, there's different hardware resources. I'm not going to go into those details, just at a very high level. What we did was build this interpretable energy predictor. So, so this is a very, very, very simple BERT model. I'm just showing you one layer, and it shows the model abstractor. So what we would do is we would predict the energy for the machine learning primitives, and then use that to learn the energy for the modules and so on until we actually get the energy for the final system. And then we also built a demo where you can actually upload your model from Hugging Face, and then we'll tell you this is how much, this is the predicted energy. Of course, there's a lot of unasked questions here. How am I going to use this to do what-if analysis? How am I going to use this to do things other than NLP? This was mostly designed for NLP. So this is just the tip of the iceberg. There's a lot more to be done in this space. Okay, so I couldn't help but use this meme. So how it started was we were using an N95 phone and trying to figure out why this 3G energy consumption was the way it was, to currently using extremely sophisticated phones. Our phones are basically like computers today, and to see how we can do a sustainable NLP. All right, so the last part of the talk is something that I'm very excited about these days. This is more relatively newer work than the rest, called accessible computing for all. And what I mean by this is, are we building applications that can be accessed equally well by everybody, irrespective of their socioeconomic background, irrespective of their abilities and disabilities, irrespective of their geographical region? And like Suman mentioned, it started really from my PhD days. I was working on these delay tolerant network. The idea here was, look, if I don't have continuous connectivity, I'm in a place where they don't have coverage, and I only have connectivity here and there, right? What kind of application can I support? Can I still support applications, and how do I do that, right? So the way we did that was, for example, this is a bus. This is called DieselNet. This is done by my advisor Brian Levine back then. But what we did was we put computers in these buses. And then when the bus goes, actually these red lines are where the bus transfers data to each other when they pass each other. And then there were Wi-Fi access points on the road. So when you pass the Wi-Fi access point, you can upload data to Wi-Fi. And then we showed that you could do web search, for example, from a bus. Right? And similarly, this is TurtleNet, where we basically had, this was a project that's headed by Jacob Sorber, my friend, and where we put these tiny modes on turtles again and ran a delay tolerant network. And so you could say this is some sort of an accessibility work, right? In the sense that, okay, how do I make applications accessible to people when you don't have connectivity? But then after that, cellular came along. This question became moot. Everybody was able to connect everywhere. And so I didn't work on this for a very, very, very long time until more recently. And recently, I've been working on two threads mainly. The first thread, and here what I mean by all is your application performance universally good? Okay. Let me give you an example of what I mean by that. This is mostly networking work, so I'm not going to talk too much about this. But anyway, this started because my student Malesh came to me one day and said, look, when I do some experiments with a phone and I use a lower CPU, things are very weird. Okay. And so that's how we started. And we said, okay, let's look at this. So what I did was I bought a couple of phones from India. And then we did this study. So what you're seeing here is the page load time. We did this for different metrics. The y-axis is different phones. So the Intel Amaze 1 and Gioni are very popular phones in India. And then on the right are Galaxy S6 and Google Pixel 2, which are popular now. The middle phones are slightly older phones, right? And we loaded the exact same page, same network condition. The page load time was 10 seconds on the Intel Amaze 1, and it was less than 2 seconds on Google Pixel 2. What was the difference? Well, the price was the difference, right? So, and we've been doing some more work on this. Like I said, I'm not going to talk about those things, but essentially it seems that these applications are becoming beefier and beefier because they think they're going to be running on more and more better and better machines, whereas there is a large fraction of population which are not going to be buying these better machines. So what are we going to do about that? Okay. So this is one aspect, and actually Santiago Vargas, another student of mine, has continued working on this. So the second accessibility angle of what I mean by for all is, are applications accessible to users with different abilities, right? So if our applications are accessible to somebody who's blind, somebody who has Parkinson's, for example. And of course, I did not by any means invent the accessibility. This is a huge area. There are conferences and part of HCI community and so on. But what I wanted to do is to bring a systems angle to this problem. What can I do from the systems perspective to address some of these issues? So again, let me tell you a little bit about how it all started. It started my student Janshu. He was working on what we call UI virtualization. And this was decidedly a systems project, right? This was at MobiCom. So, and the idea was, can I virtualize my UI so that I can take out the UI from a smartphone and then place it anywhere else on any other device? For example, in this case, I would take this and place it on a watch. And of course, the question is, how do I place it? What's the best way to put it on the watch? How do I do it without applications or programmer support? Automatically, I just have to click a button and now it will appear on my watch, all adjusted for the new space. But one of the things that we had to do, an enabling technology, and I'm not going to go into why this was an enabling technology, just take my word for it, is that we had to decouple the input from the screen. So what happens is that if you actually switch your phone off, your application will stop working and your keyboard will stop working. You can't do any of that, right? So we did something so that won't happen. And then again, serendipity at play. So my student was giving a talk at our seminar. And there was another student who did accessibility work called Syed, who's now a professor at Penn State. And he came to him and said, hey, this is very cool. Can we provide screenless interaction for blind users? Because blind users don't really need the screen anyway. And maybe it'll help save power. So we got excited about this. So we started working on this. The first thing we did was we did a user study. And it was actually eye-opening. All of the participants experienced anxiety when they heard low battery use message, okay? Because they run a lot of power-hungry applications for their day-to-day life. And also, almost all of them carried an external battery pack. So when we told them that we were going to do something like this, they were very excited. And in fact, they gave us another idea. They said, there's another problem this screenless interaction will solve for us, which is shoulder surfing. If I'm in a bus and I'm looking at my phone or interacting with the phone, somebody behind me can see what I'm doing, and that's unnerving. So what we did was, okay, fine. So this is a big, busy slide. What we did essentially was extended our system to provide screenless interaction. And so in essence, what we would do is we'll take the input event, but then we will not render anything. However, we'll do everything else that your system is supposed to do. We also integrated this with TalkBack, which is the tool that most blind users use to interact with their phones. And then we built a system called Doc Reader. That's my student Jan there. Basically, and we showed that actually this saved a lot of power because now your screen is off. You can interact as you always do. And it also avoided shoulder surfing. And the users that we demoed it to really, really liked the system. So we are now continuing to work on this accessibility space. This is led by Prerna Khanna, who's in the audience right now. And I'm not going to go into our details because this is work in progress and we'll probably be submitting somewhere, so I don't want to talk too much about it. But at a very high level, what we're trying to do is we're finding out what are the main interaction challenges. And actually, this is also with Shubham, who's also here in the audience. What challenges the users have when they have different abilities. We're looking right now at blind users and Parkinson's, people with who have Parkinson's. And then we'd say, okay, how can we now build practical systems that will make their interaction seamless? And one of my biggest takeaways is that you really need to build a system that your target population needs, not the system you think they need, okay? Because again, I'm not going to talk too much about this, but one of the things we found was most of these users, they are as diverse as a sighted population. There are people who are extremely tech savvy, those who are not. There are people who interact in a certain way with certain applications, those who want a completely different needs. And so when we build the system, we want to make sure we take into account what are their current challenges and also know who we are building it for. Is this for tech savvy users? Is this for users who may not be tech savvy but use these specific kind of applications? But the interesting thing is that there are a lot of commonalities also in this target population, right? For example, most blind users don't want to take their phone out of their pocket, especially in New York City, because they're worried somebody's going to steal it, right? And then if you talk about gestures, for example, they don't want to do gestures that are like, expansive because they think people will stare at them. So there are many of these things that is truly eye-opening for me to see what kinds of challenges they face. And so I mean, I am as much guilty as maybe others in trying to build a system that I think that, a target population wants, where that's totally not the thing to do. Okay. So that brings me to the end of the 3 threads. I'm going to talk a little bit about the takeaways, and then I'm going to go on and have a bunch of people to thank. So my biggest takeaways are that I've been actually lucky to do a little bunch of interdisciplinary research more recently than before. And I think that it lets you tackle more ambitious problems that you may not have thought of before. But the key, I think, is to understand both domains. And one way to do that is to try and make contributions in both domains. And that forces you to speak the language rather than just think of it as a black box and try and do something. The second thing is that serendipity plays a crucial role in research. The number of times I've had ideas talking to people at conferences, or attending a seminar, going to a talk is just countless. Right? And I'm sorry that I know many of you have not been able to attend a conference for the last 2 years. This is awesome that we are all here. But it's important to keep your eyes and ears open to use serendipity. And the third thing is, I think it's important to define your impact for yourself. Each of us have our own incentive system that goes beyond papers, because that helps you survive that reviewer too. Okay. All right. So before I finish, I really have to thank a lot of people. First of all, my students. I actually talked about many of my students. There are 3, Rebecca, Yi, and Shengyu. They do mostly networking work, so their work didn't feature here. So thank you to them as well as the rest. I have a great group. I also worked with Sophia Wong and Hai-Chin when I was at UW. And here I want to mention that I also have countless number of collaborators that I worked with. I don't have the space to put all of them here, but thank you to all my collaborators. A huge, huge, huge thank you to my mentors. I cannot tell how important it has been to have great mentors. My PhD advisors, Brian and Arun, I mean, I still catch myself saying something to a student and saying, oh, that's exactly what Brian would have said. That's exactly what Arun would have said. Also, huge thank you to my internship advisors. Victor is right here, and Ratul. I had a fantastic time at MSR for 3 years. I learned a lot. And they also, actually, one of the things that somebody said about always questioning the status quo, I got that from MSR, really, because they always question the status quo. Also, my postdoc advisors and at Stony Brook with Samir, because they let me grow, because I'd finished my PhD and they really let me grow. I'm very thankful for that. And then there are a bunch of mentors, but they don't know they're my mentors. I want to thank them. Lynn, Robin, Heather, Suman, Romit. They've actually always looked out for me. Since I was a PhD student, it's just fascinating that why they looked out for me like that, but they have. Of course, I've also been in awe of their research work, but they're also very kind people. And finally, I just wanted to finish with some photos. Here are some photos from HotMobile conferences. This was at MobiCom, I think. This was at an N2 Women. Here are some photos with my students, because at the end of the day, it's all about the people. Thank you.